someone I know quite well, Vladimir Dotsenko from the University of Strasbourg, and he's going to talk about F-manifolds and pre-algebras.
All right. Thank you very much for the invitation to talk at this seminar. I really wish I could do it in person in Barcelona, so that after the seminar we could go have some delicious lunch. I miss lunches, so I will talk about a relatively old result from a couple of years ago. Somehow there are two reasons for that. First, I actually very much enjoyed proving the theorem I'm going to talk about, and in some way, in the proof, many things that I've been thinking for many years converge together. So it's you will see it's a rather pretty result, but also it's a nice, its proof is a nice illustration how you can actually do some non-trivial things with operands, and also somehow right now I am in the process of writing down another result which somehow involves some of the protagonists of the talk. Probably in a month or so I would be ready to give a talk about that new result, and so somehow this talk is kind of laying ground for another talk that I hope to give at some occasion in very soon. So, well, I will start with explaining what the title means. So, pre-algebras is something that a lot of people participating in this program know extremely well. So perhaps I will start with just briefly recalling that a pre-algebra is a vector space with a bilinear operation that sends two elements A and B into A star B, satisfying A star B. It satisfies the weak associativity property. If it were associative, the difference, like I just wrote, A star B star C minus A star with B star C, if it were associative, this difference would be equal to 0. And I'm not requiring it to be equal to 0, but I'm requiring it to be right symmetric, to be symmetric in B and C. So I will write A star C star B minus A star C star B. And in principle, let me just remark that if my vector space A has homological grading, there will be some casual sign arising from exchanging B and C. It has homological grading, there will be casual signs. But I'm going to ignore that for the moment to just not make formulas excessively heavy. so I think about this identity apparadically. A, B, and C are just three placeholders, and signs only appear when you substitute instead of A, B, and C concrete elements with concrete homological degrees. Somehow, so as I said, Preilly algebras are appear in essentially everywhere, have been known to mathematicians pretty much since the works of Arthur Cayley in 1850s. So in some sense, perhaps it's maybe one can say that it's the oldest non-associative structure in the world, if one wants to have some dramatic slogan. So F-manifolds, this is something which is was invented much more recently in the 1990s, invented by Klaus Hertling and Yuri Ivanovich Manin. And somehow it's some so geometrically, so I will focus on the algebraic aspects of the story, but geometrically F-manifolds are some slightly weakened version of Frobenius manifolds that naturally appear, for example, in singularity theory. So there is a wonderful book of Klaus Hertling on singularity theory where there are many meaningful examples of F-manifolds that appear from studying singularities. But essentially, so what does one? What is an F-manifold for an algebraist? So well, let's make it a little bit geometric. So you have a manifold M, you have a tangent bundle Tm. Of course, on Tm, you have the bracket of vector fields, the most famous operation in differential geometry. That is always there. You don't need to require any conditions. Now, a structure of F-manifold is an extra operation on the tangent bundle. You want to have a you want to make the tangent sheaf the sheaf of commutative associative algebras. So you want to have product which I denote by circles. So you want to be able to commutatively multiply vector fields. So this is commutative and associative. So far, so you have a Lie bracket of vector fields, which always exists, and the commutative associative product, which is something which usually does not exist. And you want to have some compatibility relations. And of course, usually when you see a commutative product and the Lie bracket, your first reaction is probably that the compatibility relation is the Leibniz rule, so which defines the Poisson algebras. Somehow, F-manifolds, the algebraic structure that appears here, can be viewed as a weakening of the Poisson identity. And so I will give you two equivalent definitions now. This is Lie, this is commutative associative plus compatibility. And let me tell you on the next blackboard what that compatibility is and tell you in two different ways so that you can see it's a little bit better what this means. The compatibility. The first version of compatibility. You write the thing that I will denote P, X, Y, Z. equal to x bracket with the product of y and z minus the bracket of x and y circle with z minus the bracket of xz circle with y. If this were a Poisson algebra, this expression would be identically zero. That would be the definition of the Poisson algebra. And I'm going to weaken the Poisson property. So I will write the following identity. So this is the notation. I will say that this P, which is now a function of 3 arguments, it's a derivation with respect to X. Pxy of zt is equal to px zt multiplied by y plus py of zt multiplied by x. So this is a certain weakening of the Poisson compatibility of the Leibniz rule, if you want. And the second version which is a little bit more cryptic, but at the same time maybe a bit more transparent. You can write it in the following. The same identity can be written explicitly as follows. That the bracket of x, y, and z t is equal to the sum of 8 terms. It will be the sum of the 4 terms of the form x, y, z multiplied by t. So there will be the 4 terms like that. Basically, you can take each of the 4 outside the Lie bracket and minus the sum of other 4 terms. A typical term will be the bracket of xz multiplied by y multiplied by t. So you take one thing from the first place in the bracket and one thing from the second place. So there are 4 choices. You move either x or y outside and either z or t outside. So this kind of identity, which somehow looks a little bit surprising, and somehow one thing. So I will very almost immediately talk about the algebraic aspects of the story, but let me make one remark relevant from the differential geometric point of view. Somehow the difference between the left-hand side and the right-hand side in this identity turns out to be a tensor, turns out to be linear over the with respect to multiplying by functions. So somehow, if you remember that we are talking about vector fields, this is a non-trivial statement. So that this construction is not just linear over the ground field, but linear over functions. Somehow. So this is from the differential point of view, this is a tensor construction. It's all linear, and this can be checked by some direct calculation. But it's as far as I'm concerned. I asked several people, so there is a little bit of mystery here. So it's not fully understood why this is like that, and somehow, yeah. Of course, this we all invariant tensor constructions like that appear as exotic classes of some Lie algebraic homology for appropriate infinite dimensional Lie algebras. But to me, it's from what I know, this goes far beyond of what we know of the corresponding Lie algebraic homology. So it's a mystery why this thing exists. Right. So in any case, so I now, as I told you, I will switch to the algebraic side of the story. And so let me just to emphasize that, let me just say that an F-manifold algebra, F-manifold algebra, by definition, is a vector space with a Lie bracket and the commutative associative algebra structure related by this compatibility. So from now on, until more or less the end of the talk, you can forget about the tangent bundle, you can forget about the manifold, you just think about this structure. So similarly, so of course, in a similar way, people define Poisson algebras, which are a vector space with a Lie bracket and the commutative associative algebras related by the Leibniz identity. And of course, each Poisson algebra is an F-manifold algebra because the compatibility is weakening of the Leibniz rule. So this is just some source of stupid examples of F-manifold algebras, if you want. Now, let me let me tell you how the two stories that I briefly outlined, the pre-Lie algebras and the F-manifold algebras, are related. So we all know that Poisson algebras are related to associative algebras. How are they related? For example, there is the celebrated story of deformation quantization, which says that if you have a family of associative algebras depending on a parameter, then if you pass to the quasi-classical limit, if you look at the deformation infinitesimally, then the infinitesimal part gives you a Lie bracket, which is the which acts on the commute. Well, if you have a family deforming a commutative algebra, then the first order deformation gives you a Poisson algebra structure. From the operand point of view, I want to express this relationship as follows. You have the operand as of the operand of associative algebras. You have a map of operands from the Lie operand to the associative operand, corresponding to the fact that the commutator in an associative algebra gives it a Lie algebra structure. And so, in fact, this map is an embedding, as it is well known. And you can somehow use that embedding to define a filtration on the associative operand. So you can take inside the associative operand the operatic ideal generated by the Lie bracket and define a filtration by the powers of that ideal. What does it mean? This means that you consider all operations in the associative operand, operations which you can write using at least one Lie bracket, operations that you can write using at least two Lie brackets, and so on. It's analogous to filtration by an ideal in commutative algebra, which, of course, we all know very well. You have filtrations on the polynomial rings, on power series rings by the powers of the maximal ideal. Here, the ideal is not maximal, but, well, who cares? So we can define a filtration by powers of the ideal generated by the Lie bracket. What is good about defining a filtration on an operand by powers of an ideal? This means that if you take the associated graded for this filtration, the associated graded will still be an operand. So it's, well, I mean, it's a result which almost instantly follows from, for example, the Poincaré-Birkhoff-Witt theorem, is that the associated graded operand is the operand of Poisson algebras. So Poincaré-Birkhoff-Witt implies that the associated graded of the associative operand with respect to this filtration defined by the powers of the Lie ideal is the operand of the Poisson algebras. Now, I told you that the Prelli identity, the notion of a Prelli algebra is gives you some weakening of associativity. So there is a quotient map from the operand of the Prelli algebras to the operand of the associative algebras, where you force the product to be associative. Then there is this associated graded that makes the Poisson operand out of the associative operand, which I just told you. Of course, there is also a map from the operand, which let me denote F-man of F-manifold algebras, to the operand of Poisson algebras, because, as I told you, the compatibility between the product and the Lie bracket in an F-manifold algebra, it's the weakening of the Leibniz rule. So every Poisson algebra is an F-manifold algebra. There is this map of operands. And the main result that I am going to explain to you today is that this picture closes in the most obvious way, that on the Prelli operand, you can also define the filtration by the ideal generated by the Lie bracket. because, well, there is an analogous map of operads from Lie to Prelie. So it turns out that the associated graded operad is precisely the F-manifold operad. So for the filtration of the Prelie operad by powers of the ideal generated by the commutator AB minus BA, powers of the ideal generated by A star B minus B star A, the associated graded operad is isomorphic to the operad of F-manifold algebras. Somehow it's as far as I am concerned, this result is even though I presented it to you in a way that pretending that it shouldn't be surprising, because, you know, Prelie relaxes associativity, F-manifolds relax the Poisson identity, so why not? It is a rather surprising result, because somehow geometrically, the a reasonable counterpart of this story still does not fully exist. So somehow there are some recent attempts to talk about deformation quantization for F-manifolds, but from what I understand, people write some definitions, and then I don't think that there are any examples. I don't think that there are any theorems. So the geometric side of the story is wide open. And algebraically, you know, Prelie is an operad whose most elegant realization due to Frédéric Chapoton and Muriel Levernet is based on rooted trees. F-manifolds don't really have nothing to do with rooted trees, but nevertheless, since I told you that the associated graded operad is F-manifolds, this means that components of the F-manifold operad, the symmetric group action is the same as the action on rooted trees, which is surprising, extremely surprising. So it's when I first noticed, so I mean, I was prompted by Yuri Ivanovich Manin to think about this F-manifold operad when I did some calculations for the arities up to 5 or 6, and noticed that you get something that looks in terms as dimension and symmetric group action as rooted trees. I was really very much surprised and excited, and then I spent maybe 5 or 6 months thinking about it, and I was lucky to figure out how to prove it. And now, so my goal is to prove this result. Another reason why I like to give talks about this theorem is that often in our business, in the business of higher structures, in the business homotopy theory, we have to spend maybe the first 45, 50 minutes of the talk giving some prerequisites to actually be able to formulate our lovely results. So this is an instance where you can see the main result relatively early into the talk, and now I can give you some hints on how it is proved. So, of course, there is something which I want to emphasize here, that in this square the three vertices associative, Poisson, and Prelix, these are operads with quadratic relations, and so they somehow fall into the framework of the causal duality theory. So the three vertices of this square, as Poisson and Prelix, are quadratic causal operads. And the operad of F-manifold algebras is not quadratic. It's quadratic and cubic. Because the Jacobi identity and the associativity for the product are quadratic relations, of course, but the compatibility is an identity with four arguments, so it's built of three, each term is built of three operations, so you have a cubic relation, and which means that this operad is outside for a lot of operadchiks, this operad is slightly outside their comfort zone, because somehow we all like to try to use the power of causal duality to progress with what we do, and somehow probably the only example of a quadratic operad which where somehow you can understand its homotopy theory, its model, and so on, is the operad of Bataillon-Minkowski algebras, right? Which also is technically quadratic and cubic, and for the Bataillon-Minkowski operad, the path towards understanding its homotopy theory also went through the causal duality path. So there is this wonderful work of Imma, Andy, and Bruno of the homotopy, on the homotopy theory of the Bataillon-Minkowski operad, viewed as an operad with quadratic linear relations, and then Bruno, together with Gabriel Drummond Cole, used that non-minimal model to compute, for example, the minimal model of the Bataillon-Minkowski operad, and then use it to prove some deep results on homotopy theory of Bataillon-Minkowski algebra. So somehow I am not making any general statements here, but I do want to say that operads which are not quadratic are lacking general methods that would give you answers in one go, so to say. You need to put much more effort in and deal with such operads in case-by-case basis. It's not it's harder to deal than dealing with quadratic causal operads. So somehow now let me give you some hints on how this result is proved. So first of all, let me perhaps start with a very stupid thing. So in principle, so my theorem is that the associated graded operad is isomorphic to the operad of F-manifold algebras. So in fact, well, F-manifold, so here the right-hand side is at least very precisely defined. It has two generators which satisfy certain relations: the Jacobi identity, the associativity, and the compatibility. So this is more or less explicitly defined. Explicitly defined. On the left-hand side, this is a much less clear operand. So you know its size, it's of the same size as Preli, so you know the dimensions of components. But strictly speaking, you don't know, well, you also know, you also can easily understand what are the generators. So this is generated by the class of the operation, the class of the Preli product, but this operation it becomes commutative in the associated graded world because A star B minus B star A defines the filtration. So A star B individually lives in F0, B star A lives in F0, but the difference lives in F1. So in the associated graded, the Preli product becomes commutative. And then there is this operation that I will denote by the bracket, which lives in F1, survives over there. So you have the commutative product, and you have the you have this bracket. This bracket is a Lie bracket because, in fact, it is a Lie bracket even before the associated graded, since the commutator in every Preli algebra is satisfies the Jacobi identity. And the Preli product, after you pass to associated graded, becomes associative because the Preli identity saying that A star B star C minus A star B star C is equal to A star C star B minus A star C star B can be written as A star B star C minus A star C star B is equal to A star with the bracket of B with C. So this lives in F1. So somehow this means that when you go to the associated graded, the Preli product descends to a commutative operation because this thing is symmetric in B and C. And it is commutative in the associated graded. So in the associated graded of Preli, we have a commutative associative product and the Lie bracket. That's a good start, but what about the compatibility relation? What about the cubic relation between them? So why? So I'm claiming that the two things are isomorphic. I want to at least have a map of operads from the right to the left, which means that since on the right there is the compatibility relation between the product and the bracket, I want it to be satisfied on the left. How do I see that? And this is the first step where some operatic, general operatic methods turned out to be extremely useful. Namely, so there is the notion of a shuffle operad introduced by myself and Anton Haroshkin a bit more than 10 years ago, which somehow it's a way to deal with symmetric operads while being more or less oblivious to the existence of symmetries. If you regard a symmetric operad as a non-symmetric one directly, you will run into some problems. If you consider a symmetric operad as a non-symmetric operad, it becomes the structure is not rich enough. So, for example, delightful result due to Paolo Salvatore and Alberto Rasso is that if you take the Lie operad and consider it as a non-symmetric operad, it turns out to be a free operad on infinitely many generators. So all the magic of the Jacobi identity is completely gone, and you earn the infinity of somewhat untractable generators. So it's passing to non-symmetric operads is not a good strategy. Turns out that shuffle operads allow to forget exactly the unnecessary things and remember exactly the important things. So somehow, so you have the symmetric operads, you have the non-symmetric operads, and you have the shuffle operads. And so the shuffle operads are somewhere in between on the way of forgetting all symmetries. So you don't have the symmetries permuting the arguments anymore, but the monoidal structure that you consider is still rich. You do not allow only non-symmetric compositions of operations, but all possible shuffle compositions. I won't explain to you how it works exactly. I invite you to, well, many of you perhaps know it already, and those who don't know, there is my paper with Anton Haroshkin called Grobna Basis for Operads. There is my book with Murray Bremner called Algebraic Operads and Algorithmic Companion. It's powerful methods, which is reasonably well explained in those sources, I hope. So I already said that my paper with Anton is called Grobna Basis for Operads, and indeed we originally coined this notion to define Grobna basis for operads, to say how to have for each operad an approximation which will be an operad with monomial relations. If you do it with symmetric operads, you won't be able to do it really, because, for example, the operad Lie cannot be replaced with an operad with same dimensions and monomial relations. Because if you kill one term in the Jacobi identity, then because of the symmetries, you kill them all. With shuffle operads, you can do Grobna bases. And somehow, so originally when I was thinking of this F-manifold operad, I wanted to try and at least compute its dimensions in low arities. So I took the calculator for operatic Grobna bases and started calculating. And somehow it turned in arity, so for a certain ordering, in arity 4, I found a new element of a Grobna basis which looks as follows. It looks like this F identity. It looks like the compatibility between the Lie bracket and the commutative product, plus terms using two Lie brackets. So somehow what happens is that in F identity, I should probably bring it to you the definition. In the F identity, you have, it's an identity with 4 arguments where you use Lie bracket once and the commutative associative product twice. And in if you take now, sorry, I need to, I told you right now the statement, which is a little bit, excuse me, I should say, excuse me, I want to understand the associated graded of the Prelie operand. So it has the generators which comes from the Prelie product, the coset of the Prelie product and the Lie bracket, and then somehow you take the Prelie identity which you write in terms of these guys, and you start computing the Grobner basis for the Prelie operand for Grobner basis for Prelie. Using these generators, the sum, the product which is AB plus BA, and the Lie bracket AB minus BA. And for the Grobner basis with these generators, you get a new element of a Grobner basis in arity 4, which is F identity up to terms using the 2 Lie brackets, which means that in the associated graded of Prelie, the F identity is satisfied, because in the associated graded, we look at each level of filtration modulo the deeper levels of filtration. And F identity, all terms have 1 Lie bracket, and here there are terms that have 2 Lie brackets. So in the associated graded, this will disappear, and in the associated graded, F identity holds. So this is the first step. You observe that using operatic Grobner basis, you can actually discover the F identity by considering this filtration on the Prelie operand. That's a great start, but of course, this just means that there is a map of operands. So there is a map of operands from the F manifold to the associated graded of the Prelie. And of course, you can even convince yourself immediately that this map is surjective, because the associated graded of Prelie is generated by the symmetrized and the anti-symmetrized product. We just, in the F-manifold operand, we have only the identities associativity, Lie bracket, and the F identity. So there is a surjective map. How to show that this map is actually an isomorphism? The argument goes as follows. I am going to show that it is enough to show that the dimension of each component of F-manifold of N doesn't exceed the dimension of Prelie of N, because this surjective map gives you a lower bound, and independently I will establish an upper bound, and this will prove an isomorphism. Great. How to prove that? Here, once again, you need some methods of how to deal with operands. So somehow the intermediate, one intermediate result is that there is a surjection from onto F-manifold operad from an operad which I will call just O, and this operad is built of the commutative operad and the Lie operad, so you take the coproduct, and just impose the relation that AB commutes with CD. So you just take the left-hand side of the F identity, you degenerate it into a monomial relation. So this, I shouldn't denote this by arrow because it's not a map. So this is rather this. The fact that such a surjection exists, this uses some also some writing methods for operads, for shuffle operads. So essentially also uses shuffle operads in Grosvenor basis. So this is the first step, that there is a surjection like this. Now, the last step is to estimate from the above the dimension, to estimate the dimensions of components of the operad O. And for that, I am going, so, you know, if we were dealing with the Poisson operad, excuse me, so for the Poisson operad, something like that, you can also play this game. You can say that you can replace the Poisson operad by the operad with the monomial relation, saying that something like this, that the bracket of A and B with C is equal to 0. And you can say that that there is a surjective map between some operads. So this is related to what in the operatic community is well known and well understood as distributive laws between operads. So you have this identity which is a trivial distributive law, and then the Leibniz rule is a non-trivial distributive law between the commutative operad and the Lie operad. Of course, for F-manifolds, the story goes beyond the distributive law because the F identity is not quadratic. But it turns out that if you have any two, if you have P and Q which are quadratic Joule operads, and you define a new operad where you take the coproduct of P and Q and impose the relations of the form, well, let me draw them like this. Actually, I will, so you impose monomial relations where at the root vertex you have a generator of one of the generators of P, and at the next level you have some generators of Q. So I put here, of course, for commutative and Lie, the generators are binary, but a priori you might have generators which are more than binary. So for this reason, I put here a ternary operation. So for the case, for our case, all generators are binary, so it will be, but it's a more general result. So this is somehow some new construction. I don't know. I don't want to give it any name. I think that perhaps I gave some name. I said some kind in the paper almost composite product or something like that, which I don't like. So it's about the meaning of this is pretty straightforward. This is what we do. So it turns out that such operand admits always an explicit minimal model. So whenever P and Q are quadratic Joule, even though the operand that you built is now quadratic and cubic in our case in general, well, not quadratic anyway. Even though you built this non-quadratic operand, you can nevertheless give it an explicit minimal model which is built in some reasonable way from the co-operand structure of the structures of the Joule dual operads of P and Q. You can write an explicit differential at squares. You can construct some space, the space of generators of the minimal model, and write an explicit thing that squares to 0 and show that you get a model. And somehow, and then using this explicit minimal model, you can compute in a certain way the dimensions of components of P and Q by some standard methods of power series inversion, because the generating function for Euler characteristics for components for the space of generators of minimal model is compositional inverse of the generating functions for dimensions of this operand. That's a general fact, which is well known. And so using this explicit minimal model, you can establish that the dimension of O of n is equal to n to the power n minus 1, which is exactly the dimension of the Prelay of n. So you need to look at this minimal model, for which I don't have time to write it, but it's a simple construction. If you know very well how to handle the distributive law case, the quadratic case, you need only a little bit of imagination to construct the minimal model in this case. And so as a result, you obtain the dimension formula for the operand O. The operand O gives you an upper bound on the dimension of the F-manifold operand, so you have the desired upper bound on the size of the F-manifold operand, and which means that the map from the F-manifold operand to the associated gradient of Prelay is really an isomorphism. So you see, it's a nice. As far as I'm concerned, well, I like this proof because it combines many. So figuring out how this proof works teaches you a lot about operatic calculus. You use shuffle operands, you use operatic Grobner basis, you use some homotopical algebra, you construct minimal model, you do some computations with Euler characteristics and so on. So it contains inside it a lot of nice machinery of the operatic calculus, and it leads to this rather enjoyable proof of this cute result, I think. So I think that it's a good moment to stop. After all, I accomplished my goal of telling you what the main result is and giving some reasonable indications on how to prove it. So I'll stop here and I'll thank you for your patience.
Thank you very much. Thank you for this very nice talk. Is there any question? So feel free. If not, I have a question, sorry.
Right.
So, okay, you said in between Lie and As, so the operand of Lie algebras and the operand of associative algebra sits pre-Lie. Okay, fair enough. So by skew symmetrizing the pre-Lie product, we get a Lie bracket. There is another one, an even weaker one. So I'm looking for an even weaker or more general statement than the one you have today. Let's consider, alors, there are two generalizations of pre-Lie. The first one is Lie admissible.
Yes.
So do you have a definition of what could be the analog of F-manifold for if I consider Lie admissible instead of pre-Lie? You see what I mean? I take Lie admissible,
Yes.
filtration with Lie bracket. What is the
Yes. Right. So I am going to disappoint you, perhaps,
No.
if you take the Lie admissible operand and take the associated graded with respect to the ideal generated by Lie, the resulting operand is the same. It doesn't change.
Okay.
Because the Lie admissible operand is a free product of Lie with commutative magmatic operads. So, and because it's the free product, taking the associated graded with respect to filtration does absolutely nothing. So this way you don't get any new exciting results.
I'm not disappointed. I'm very happy. Because I think that Lie admissible is not the good guy I wanted to consider. So let me tell you what I have in mind.
Right.
Pre-Lie, you gave the definition as a quadratic operad, but the beautiful result is that, you mentioned Frédéric and Muriel, is that the pre-Lie operad is the operad of rooted trees.
Yes.
Higher up, in some sense, this is destroyed. This is a low-dimensional phenomenon. I could generalize pre-Lie into Lie admissible, but then what takes the place of rooted tree? And this is where the party gets destroyed. What we want to consider for being the graphical analog of rooted tree is of kind of pro-operatic trees. This is the operad that I call D-graph.
Yes.
So a certain graph operad.
Yes.
And this graph operad is not Lie admissible, okay? There is one which is slightly bigger than the other one. So my real question would be, instead of considering the rooted tree operad, pre-Lie, I want to consider this graph operad. And now, do you know what is the analog if I mode out if I take the graded guy?
I see. That's a great question. That's a great question. And I don't know a satisfactory answer. Thing is that for all versions of some kind of graph operad you are talking about, you get an operad which is which I think is infinitely generated. So it's quite difficult to deal with. So that's another thing that breaks. I mean, if you consider rooted trees, they are generated very economically just by the binary operations. For in general, the graph operads are infinitely generated. So I never dared to do some computations for associated graded. I think it's a potentially interesting but an extremely difficult question.
I completely agree with you. That's the main difference between this graph operad and the Lie admissible. Lie admissible admits this skewed presentation, but when you enter into this directed graph operad, it admits much more generators. So
yes.
Okay, well, too bad for another life. Is there any other question? Feel free. No. So maybe I can thank Volodya again.